Hey, welcome everybody. Alright, Mr. Klinkerman here. We're starting section 4.2, which is about solving exponential equations. Two goals in this section. The first we're going to address in this video, which is that you will solve equations of the form ax equals b, a to the x power equals b to the y. Alright, now just quick, an example of that. It might be the equation 5 to the x power is equal to 25 to 3x plus 1 power, something like that. And the idea is that, first of all, this is an exponential equation because of where the variable is located. The variable is part of an exponent. And when the variable is part of an exponent, that's what makes an equation an exponential equation. Alright, so that's kind of a brief introduction to what we're doing here. Let's go ahead and take a look at some examples. Alright, and what we're going to do particularly is we're going to solve exponential equations using what I don't know if it's an official name, but I call it the equivalent base method, in which what we're going to try to do is to write the expressions on each side of the equation as powers of the same base. And now this is going to require you to know some powers. Alright, you're going to need to know powers of 2, powers of 3, powers of 4, 5, 6, 7, 8, 9, 10, maybe even some for 11 and 12 and so forth, if you're going to be able to do all of these things with and without a calculator. Alright, now I want you to look at the base on either side of this equation and think about, is one of those numbers a power of the other? And if you know your powers of 6's, you know that 216 is 6 to the third power. And so where we're going to begin with this is we're going to rewrite that 216 as 6 to the third power, as such. Alright, leave the 6 to the x minus 2 power alone, and make that 6 to the third power on the right side of the equation. Alright, now if these two expressions truly are equal, as the equation tells us they are, then now since they have the same bases, the only way they can be equal is if the two exponents are equal to one another. And so what we're going to be able to do then is set this exponent there equal to this exponent there. And we'll get x minus 2 is equal to 3, so x is equal to 5. And then you can check, you don't necessarily have to every time, although it's always a good idea. 6 to the 5 minus 2 power equals 6 to the third power, which equals 216. There we go, real simple. Make each side of the equation a power of the same base. Try another one. Alright, you see the equation there and you might think, well, this one is not a fraction and this one is a fraction, so how in the world are we going to write those as powers of the same base? Well, let's start this way. I think you know that 25 is 5 to the second power, right? So let's write this as 5 to the 1/2 x power still on the left side of the equation equals 1 over 5 squared. And if you know your laws of exponents that you started in section 4.1 that you learned last year in Algebra 2, you know that if you have 1 over 5 squared, or actually anything, in the form 1 over a to the nth power, that's equivalent to a being raised to the negative nth power. In other words, we can write 1 over 5 squared using a negative exponent. And that's going to be very helpful to us here, because when we do that, now we'll have both sides of the equation written as powers of the same base. That'll be 5 to the negative second power on the right side of the equation. And now that the bases are equal, we can simply set the exponents equal to one another. Now we've got our answer. Alright, and indeed, 5 to the 1/2 times negative 4 power equals 5 to the negative second power, which equals 1 over 5 squared, which equals 1/25. So you know that our answer there is correct. Alright, we're going to try some more. Each is going to increase in difficulty level, but the idea is the same. We're going to get the expressions on either side to be written as powers of the same base. I encourage you to try these on your own before you see my solutions. Alright, there we go. See what you can do with this. Alright, what you should have noticed is that both sides of the equation can be written as powers of 10, like this. And so, of course, you can set the exponents equal to one another. And then use the skills that you already have to be able to solve the equation. In this case, that's a quadratic equation that we ended up with. We can set it equal to 0. You can factor, and you're going to end up with two different solutions to that equation. X could either be equal to -4, or x could equal +1. Try them both out. They'll each work. All right? Increase the difficulty level a little bit more. Let's go. Now with this example, the reason the difficulty level is a little bit higher is because 27 is not a power of 9. However, both 27 and 9 are powers of the same number. I think you know what number that is. If you do, go ahead and try to solve this on your own. If not, stick around and just watch what I do and then try to solve after this first step. Alright, so when I'm saying that each of these numbers 9 and 27 can be written as powers of the same number, those are both powers of 3. 9 is simply 3 squared, so I could write the left side of the equation as 3 squared to the -2x power. 27 is 3 to the third power, so I can write that as 3 to the third power to the x minus 1 power. Okay, and what I'm going to do from there is apply a law of exponents. When you raise a power to a power, remember you multiply the exponents. So I'll do that on both sides and get 3 to the -4x power equals 3 to the 3x minus 3 power. That's a binomial times a monomial, so I've got to remember to use the distributive property when I multiply them. And now I've got the equal bases on each side. I can set the exponents equal to one another. -4x equals 3x minus 3. So -7x equals -3. And then x is going to be equal to 3/7. A little bit tougher to check, but I think you know the method well enough now to know that that works. Great. Got one more example for you, and this one's going to be really tough. Let's check it out. I have no idea why that goal is written at the bottom, but let me erase that real quick. What's going to make this one a little bit tougher is not necessarily the fraction that you see on the right side of the equation. That just makes it look more difficult. But the fact that on the left side of the equation we've got a product now. All right, we don't just have a power, but we've got a product. Now, I can't multiply 16 times 4 right here because I have to be able to use the exponent for the 4 before I can multiply by anything. That's just order of operations. So, my first goal here is I'm going to try to make sure that I only have a number being raised to a power on this side. In other words, I got to get rid of this multiplication. And so I'm going to do this. I'm going to multiply both sides by 1/16 rather than dividing by 16, and I think you'll understand why I do it that way here in a second. Alright, so check this out. Now I've got 4 to the 2x plus 1 power, okay, because I multiplied the left side of the equation by 1/16 and that canceled out to 16. And on the right side of the equation, I'm multiplying 1/16x times 1/16. Now, I wanted to multiply by 1/16 rather than divide by 16 because you know how to multiply 16 to the x power with 16. With a little prompting on my part anyway. What I'm going to do, since we're going to be multiplying powers at the same base, is make sure that I know what the exponent for each of those terms is. So that's going to be 16 to the first power. Alright, and of course 1 times 1 is 1. That's me multiplying the numerators together. And the denominators, I can multiply those together, and I want to add the exponents. That would give me 16 to the x plus 1 power. Alright, now we're almost to the point where we're ready to make each side the same base. Let me go ahead and do this. You notice that 16 is a power of 4, hopefully. So let's write that 16 as 4 squared. And we'll have 4 to the 2x plus 1 power equals 1 over 4 squared to the x plus 1 power. Alright, so then 4 to the 2x plus 1 power is going to equal 1 over 4 to the 2x plus 2 power. Alright, I raised a power to a power, so I multiplied the exponents, and since that was a monomial times a binomial, I used the distributive property like on the previous example. And then finally, I'm going to make that 4 to the 2x plus 1 power equals 4 to the negative 2x minus 2. If I'm going to rewrite this so that it's no longer a fraction, I had to change the exponent to negative, and so I had to multiply the entire thing by negative 1. Alright, now I'll work over to the left here. We can, of course, set the exponents equal to one another now. So 2x plus 1 equals negative 2x minus 2. So 4x would equal negative 3, and x would equal to negative 3/4. Alright, so as long as you can make each side of the equation a power of the same base as it was with 4 here, then you're going to be able to solve an exponential equation. There are certainly instances where that's not possible, and we'll learn how to take care of those later on in the chapter. Thanks for your attention. Good luck with all this. See ya later.